So this approach has interest in several ways. One is historical, but that's not my main interest at all. Another one is pedagogical. It's introducing material to people who have never taken it. But there's an additional reason for it, which is giving certain intuitive understandings of some of the equations that pop up in general relativity. And I remember my own surprise when studying it first. After doing all of this formal differential geometry, suddenly everything reduces down to Newton's equations of gravity. And it wasn't entirely clear to me for some reason that it was exactly going to happen. It looked like a miracle. What I do is start from Newton's equations of gravity and build up to general relativity. Now, of course, you can't actually derive equations of a higher level theory from a lower level theory. That's obvious. But it's very surprising how similar the equations are when you understand the symbols in the equations a little bit differently in an intuitive way. There's another additional reason that might motivate learning this, which possibly might help young researchers if they're looking for some new theory. The idea is how to go from an existing theory to some as yet unknown theory. Now again, obviously it's impossible to learn the unknown from the known directly. But once one sees how surprisingly similar the equations, for example, for spherical symmetry are in general relativity and in Newtonian gravity, maybe one can develop some kind of intuition as to how one can recast the existing formulas of the theory, for example, for situations of very high symmetry, into something which is actually even more widely applicable, more general. And the best way to explain what I mean is simply to just start out from the beginning. What I'm going to do is start with the challenge of finding some kind of a mapping or some kind of relationship between geometry and dynamics, just ordinary Newtonian dynamics. And I'll start with inertia. What is an inertial particle? Clearly it's going to be a straight line. Every student can understand this, even in Newtonian dynamics, even in high school, that this is an inertial particle. What's nice about this, of course, is that this is uniquely mapped. Geometrically, the concept of straightness in this space, or this diagram of dr, uniquely maps to an inertial particle, as opposed to in a, let's say, xy diagram, where a straight line does not map to inertia. This is just a straight line. It could be this straight line. It could be an accelerating particle moving back and forth and so on. So right away one can see that when you add time, and you have space and time, and I won't call it necessarily space-time because it's not special relativistic, right? You don't worry about this angle and the speed and so on. You can see that this maps directly to the concept of inertia. And you can now state the principle of inertia as particles which have straight world lines continue to have straight world lines, and you can extend it out unless there's some kind of a force. And it's kind of the force that bends the world line. Obviously, a curved world line means acceleration. Okay? So, if this is r, just naively, again, in this TR diagram, if you have an accelerated particle, I'm not going to worry about the direction curving in this way or curving in that way. You have a curved world line. What is the ordinary calculus curvature of this world line? If you think in terms of r of t as the world line, rather than t of r, let's say, then simply r double dot is the calculus curvature of this line, the second derivative. The derivative is the speed, and the second derivative is the acceleration. So we have a very nice mapping. We have acceleration is equal to second derivative r, which is the world line curvature. Right? So again, I'm not talking about special relativity. I'm not talking about anything like that. I'm talking about purely Newtonian physics. You can say that acceleration is world line curvature. Okay? I can then write F equal to ma, or A equals to F over m. And I can say that this is world line curvature. So world line curvature is the force over mass. Okay? Now, if you had a bunch of particles in some region of space at a given time, and they're all moving with different accelerations, and maybe some are inertial and so on and so forth, so we can always define their accelerations by world line curvature. Of course, acceleration is a vector. This world line curvature was not defined geometrically precisely, and I won't bother doing it because one gets to something entirely different later. But naively, again, you make this definition. Now, imagine something wild, something crazy. I would take something, for some reason I would warp the time in this region of space. Okay, I'm going to warp it in such a way that this world line will uncurve. Now, the first imagination you have is maybe I'm going to curve the world, this timeline, and uncurve this as a result. But it doesn't have to be that. It's just I'm going to warp the time in some way that this is going to uncurve and become a straight line. Now, of course, it's a straight line in this warped time. So the more general term, of course, would be geodesic from the language of curved surfaces. There's no clear relationship here between curved surfaces, except for the fact that here you have a curved line, and we know that the equation for the straightest line, the geodesic equation, can be recast in curvilinear coordinates and so on. So one can imagine that you have the language of curvature here. There's a curved line. You're doing something to warp the time. That warping will cause an uncurving of this world line, and therefore maybe we can call that warping curvature. But we'll get to that later on. And again, this is just a naive and wild proposal. It turns out, of course, that using differential geometry, one can do this rigorously. Now, what would happen to all these particles? You have particles accelerating in different ways, moving with inertial speeds in this region of warp time. What is going to happen to them when you suddenly warp it? As a result of the warping, the inertial particles which have straight world line are suddenly going to have curved world lines. Some of the particles which have curved world lines are going to uncurve and have straight world lines. If you warp this time in a certain way, then there's going to be some specific set of particles with a specific type of acceleration somehow related to this. Right? They have some kind of an acceleration which is a world line curvature. You have an intuition that there's going to be some characteristic of this warping which is going to map to this value. The amount of curvature here will correspond to the degree of the warping of time necessary to straighten it. So to whatever, let's say you warp it by an amount, whatever it is, one particular set of world lines will uncurve and become geodesic. And all the others won't, because it's not the right kind of warping. So what you'll see is certain particles that are allegedly accelerating will suddenly feel allegedly inertial. And some of the particles which were inertial, or all of the particles which were inertial, will suddenly start accelerating. Now, one of the interesting features of this is that it's, of course, independent of the characteristics of the particle. If the reason for the acceleration is this warping of the time, and the warping of the time has nothing to do with the particles, it's the time itself, then clearly all particles will be equally affected. Okay? So in other words, all inertial particles will suddenly accelerate in the same way. Now, what I do is I can simply pose it to any kind of student who studied mechanics and ask them, is that at all possible? Does it make any sense that you'll have inertial particles, and as a result of some kind of field, suddenly they all accelerate, and they all accelerate in the same way, irrespective of their characteristics? Is that at all physically intuitive? And the answer, of course, comes up very quickly. Yes, that's gravity. Now this one I'm going to call RT, let's say, because this is the world line curvature. It's in the RT diagram. All right? Now we can take it one step further, as I said before, about warping time. And now we're talking already about a differential geometry theory. Okay? And we know that there'll be some characteristic in that warped time which will map onto this. In other words, to the degree that this world line is curved, we're going to warp the timeline in such a way that it straightens this out and makes it geodesic. So instead of this being curved, the geodesics of that warped time or space-time are going to have some kind of... Now, of course, a geodesic by definition is the straight line, so it doesn't make sense to call it curvature, but if you took, for example, a curved surface and you drew a geodesic on it, the straightest possible line, if you looked from outside the surface, you could get some kind of curvature. If you're talking about intrinsically, then of course you wouldn't really be able to define that curvature. So this is a not really well-defined type of curvature, but you know that there will be something in that theory, in the differential geometry description of that theory, which will have something to do with the geodesics in this warped time or space-time, and that will map to the acceleration, which is the world line curvature. A was this gamma, this world line curvature, which in the higher level theory is going to be a geodesic curvature. A measure of the curvature of the geodesic. It's the straightest possible line, but it has some kind of curvature, and we can't really define that curvature except from the outside, which we don't want to do. We want to stay intrinsic, but we have some kind of intuition about it.
Not always you have a method. You say that not always have not for every acceleration you have a method.
But this is all this worked only for gravity, because only for gravity can one describe the field as a function of the space or the space-time. In every other field, every other force, you can't say that the effect is the same. You have a force, and depending on the mass of the particle, the charge of the particle, the velocity of the particle, that will tell you what its effect is. So it doesn't make sense to say that the effect is a property of the space, of the medium, of the space-time. This whole model doesn't work except when you can say that the result is totally independent of anything but the source. The source gives rise to a field, and that field totally determines what the effect will be. Obviously, that determines what the acceleration will be. It doesn't determine what the velocity is. The velocity is simply initial conditions. That's not interesting. But only for gravity can you do that. And only, therefore, for gravity can you map all that using curvature. Because curvature is a curvature of the space, or of the time, or of the space-time. It doesn't have anything to do with the particle that's in that space-time. An acceleration, which is a world line curvature, you have an intuition that there's going to be some characteristic of this warping which is going to map to this value. The amount of curvature here will correspond to the degree of the warping of time necessary to straighten it. All right? So we already have now a different theory. We can look at the same equation and say, at least in those situations where Newtonian gravity is correct, we will expect that whatever this higher level theory built on differential geometry and so on, whatever it is, it will map and reduce eventually down to this equation, something very much like this equation. So now one can ask, what might be the field theory of such? What might be a field theory for this? So we have a differential equation that is a field equation for the acceleration, and you all know that we can write it as divergence of A is equal to rho. Okay. Again, we don't need to use force over here because we have an equivalence principle. We're talking about the acceleration. We have an acceleration field. And the differential equation, just in Newtonian gravity, but formulated differentially, would be divergence of A is equal to rho. In vacuum, of course, where this is 0, this is a trivial equation. And we always want to deal with local field equations, and in fact, this differential recasting gives us local equations over here, because we're talking about even in the exterior of a source where there clearly is a field. On the right-hand side, we have a 0 source. It doesn't lead to no phenomena. It leads to k over r squared. The k could be 0 if there's no mass in the boundary condition matching, or it will be gm if there is a mass. An interesting thing, what are these 1 over r's? They come from the fact that, of course, we have this angular thing over here, right? What is this a measure of? It turns out to be a measure of the curvature of these curvilinear coordinate lines, right? The theta and phi lines are circles, right? What is the curvature of a circle? It's defined as 1 over r. The larger the circle, the larger r, the less curved it is, the more it seems, so it's like the Earth's surface seems to be flat, because r is very, very big. It goes as 1 over r. The curvature goes as 1 over r. The smaller the circle, the more you'll notice the curvature. Okay? So it's inversely proportional to r. This curvature, right, it's a measure of the coordinate line curvature. And in differential geometry, that's the connection. The connection, now we'll talk a little bit more about, I kind of hinted at it before. The connection is a set of quantities in any space that tells you how things are curving. Okay, just not to put it non-technically, right? How things are curving. If you have curvilinear coordinate lines in a flat space on a flat surface, you know that your geodesic equation, for example, is going to look funny. It's going to have sine thetas and r's in there and so on and so forth, even though it's a straight line. If you use Cartesian coordinates, it will simply be x double dot equals 0, or y double dot equals 0, z double dot equals 0. If you're going to use r theta phi in a flat surface on a flat space, you're going to get r sine thetas and so on popping in there. All right, because your coordinate lines are curved. The connection also tells you on a curved surface. If you draw the straightest possible line on a curved surface, even though it's a straight line, the surface is curved. There are going to be functions creeping into the equation of the geodesic. Even if you use Cartesian coordinates, x, y, and z, right, you're going to find that you can't write x double dot is equal to 0. You're going to get x double dot y plus y squared. I don't know. Something is going to happen here. You can't write just this on a curved surface. And if you use even curvilinear coordinates, r theta phi on this curved surface, you're also going to get r squared sine theta squared. You're never going to get just, x double dot equals 0 or y double dot equals 0. And in a curved space, the same thing happens, of course. You can't get away from having these other functions pop up. All right? So the connection is that mathematical quantity that tells you how that happens, so that you can write the equation. For example, the straightest line equation that tells you, okay, put this in front of the x, and put this in front of the y, and put this in front of the z. All right? And one of the components of the connection, even in a flat space, on a flat surface, if you're using curvilinear coordinates, is this 1 over r thing, which comes in very simply from the curvature of these coordinate lines. And it then manifests itself in the divergence. What does the divergence do? Of course, we know from Gauss's law, right? You have, let's say, flux lines coming out, right? You take an imaginary surface. The surface gets larger, the area gets larger, of course, but the field lines are more spread apart. So given the same angular distance between two lines, as you go further out, the field lines are weaker, but the surface is bigger. Divergence equals 0 means that one counters exactly the other. That as you go out further and further and further, you get the same amount totally. Because even though the surface is bigger, it's weaker. What does that mean? That your charge is the same. Right? And something has to be, something is conserved. One effect is countering the other effect. So if you're measuring the flux, what you're measuring is like the source charge. And that's the same. Be the mass of the electrical charge. Sorry. An equation which takes the sum of these three things and adds them together and says that they're 0. Okay? A prime plus 1 over RA plus 1 over RA equals 0. This changes in one direction, these two change equally in the other direction. Okay, these become smaller, this becomes bigger, and the sum of the two cancel each other, leaving 0. And that's how we get around the problem in a local theory where you have 1 equal to 0, you have no theory. It's a combination of these quantities which vanishes, not the quantities themselves. Okay, now we're going to rewrite this equation, but we're going to now rewrite it with this 1 over r written as a connection coefficient, because that's really what it is. And I'm also going to rewrite it using this a prime, writing this a prime as a curvature. It's really the world line curvature, right? Which we know is going to be a measure of the geodesic curvature in this curved time or curved space-time theory. So really this equation is all about connections, all right? This a prime again, I can substitute the gammas purely in Newtonian geometry and say this is simply an equation for the world line curvature, right? All right. So we have this very nice, simple differential equation, a field equation for the acceleration, or for the world line curvature, or potentially, possibly, in this higher level theory where one has a warped time, which maybe one can call curved within the context of maybe space-time, and one might expect that at least in those situations where Newtonian gravity gives the correct answers, this other theory, which is built in a rigorous way in differential geometry, will reduce down to an equation which looks very similar to this. And then I can adapt it to the more rigorous theory, which I haven't yet developed, of course, and say that in that theory, I expect that at least in the Newtonian regime where Newton gives the right answers, that we're going to get an equation here where this will be something like r plus 2 times something to do with the geodesic curve over r equals 0. The same equation, just reinterpreted. This straight line on the blackboard, but if I'm using curvilinear coordinates, for example, spherical polar coordinates, then there's a curvature to these coordinate lines. That curvature introduces into the straight line equation things like 1 over r or r squared. And if you write this equation in curvilinear polar coordinates, you end up with 1 over r something sine theta plus whatever. And it's just a straight line. But that's because these things are curved. Okay? So, and those things, this 1 over r's and the r squared, are all expressions of the connection of the space. This is really like an r theta, this 1 over r. It has nothing to do with time, it's just the curvature of this coordinate lines in a flat space and so on. Okay, then r theta over here times a, which is this guy, this rt, plus gamma, this one will be the r phi times rt. All right, this is basically, what is this? This is the divergence of what? The divergence of a, the divergence of this guy, this rt. And again, this is not really well defined because this is not a vector. Divergence is a vector operator. But something like this. We have divergence of this gamma rt, which is a connection coefficient. Okay? Either world line curvature in Newtonian gravity. I can read this equation, in other words, in two totally different ways. One, in Newtonian gravity, purely Newtonian gravity, I added nothing beyond Newtonian gravity. No special relativity, no general relativity, no warped space-time, nothing, just purely Newtonian gravity. I say the divergence of the world line curvature, maybe the acceleration, is equal to the acceleration of world line curvature prime plus these guys 1 over r times this. This is a purely classical Newtonian gravity, nothing here. I can also read it as a speculative equation of what I might expect possibly in this higher level theory that I'm hoping to create based on differential geometry, where this is not going to be any more a world line curvature. It's going to be the geodesic curvature in a warped time or warped space-time. Now, these things still remain the same. Of course, in the future theory, in correct theory, we're going to have curvature of space also, not just warping of time. And then these guys, even though they remain 1 over r, the r is the art of a curved space, but that's something entirely different. Even leaving aside that, I have a much more sophisticated abstract theory taking place in a warped time, somewhere in the context of space-time. And in that warped time, I have something that's going to be the equivalent of a divergence. Right? I have to define that in differential geometry, what that is. The thing that will reduce to a divergence in flat space-time. Divergence of this geodesic curvature component. It turns out that for Schwarzschild, in fact, you get exactly this. It's exact Schwarzschild coordinates, which is surprising. One has to figure out why that happens. Okay. Now, there's a problem with this development, and the problem is really based on the very fundamental aspect which we started with, namely the equivalence principle. Okay? The equivalence principle tells us that as a particle is falling freely in its own frame, there is no acceleration. Right? Locally, one will not experience acceleration. Now, if you don't experience acceleration, you can't build a field theory locally because there's no phenomenon. And we always want to deal with local field equations. Okay, so we have a problem now. What do we do? How do we get a theory if in a free-falling frame, to get our local theory, there's no phenomenon? All right? Now, I assume that most people here know what the answer is, but let me ask maybe the students or the people who are the least senior, who have only taken maybe general relativity once or something like that. Would you be able to easily answer? Let's say, would everybody be able to easily answer what is the solution? Like, what is the phenomenon? What do you do with the fact that this whole theory is built on the equivalence principle, and yet from the equivalence principle we know that there's no phenomenon locally. So how are we going to get a phenomenon? How are we going to write? What are we going to write a field equation for if the acceleration vanishes? I mean, in theory, this A vanishes in free fall. Correct? I don't know if this is obvious or if I lost everybody. Okay, would you? With that? Fast. Fast? Fast. Okay. Was everything, though, understood up to this point? I mean, I zoomed through it because you all said that you were experienced that this generally takes an hour on its own just for students or something like that. Is everything clear? Or maybe you want to ask some questions? Everything's clear? Okay. So if you go to free fall frame, it indeed will happen that you will not notice your acceleration locally. However, if you have two particles falling adjacently of whatever mass, they do fall with the same acceleration. However, they don't fall with exactly the same acceleration unless they're exactly at the same point. If one is above the other, clearly, then the one that's closer to the source is going to have a greater acceleration, obviously, and this one will have lesser acceleration. What is going to happen if you have two particles with different acceleration, one larger than the other, but both along the same line, they're going to separate, obviously. So if you're freely falling, two people, one right on top of the other, you will have a relative acceleration between them. You will each one see the other one accelerate away from the other. Okay? If you're falling alongside each other above a spherically symmetric source, all right? Now, you're both falling straight down, but that's radial. Okay? You're falling radially, and so you're not falling in collinear straight lines, right? You would imagine first that you're both falling, straight down, but you're not. You're falling radial. Now, if you're very close together, it's going to be a tiny angle over here. It's going to be a very, very tiny difference. But there is a difference. One acceleration is like this, the other acceleration is like that. If you subtract them, you do have a relative acceleration between them. Now, is this necessarily an acceleration, or might it be a constant velocity? If you have two cars moving along perpendicular roads, right, and they're moving like this, right, and hopefully there's a tunnel or a bridge over here, right? As you look at one from the other, what do you see? If they're both moving at constant speed, then the vector joining the two, right? The vector joining the two, the distance will get less and less. But what is the rate of change of this vector? If they're both moving with constant speed, it'll be a constant change. If they're accelerating, even if they're moving exactly at the same speed at any given instant, then there will be a relative acceleration between them. Okay? Since these two are accelerating, there will be a relative acceleration of this distance. Okay? Now this is something that can be noticed in a kind of almost local frame. It's not exactly the local frame anymore because you have an extended frame. You need to have a few particles. Let's say you have an array of particles now falling, and you're going to measure the relative acceleration of these guys due to the radial difference and the angular difference here, and the acceleration of these guys due to the radial distance difference. Okay? And that gives you a phenomenon. But again, not exactly locally. So on the one hand, the equivalence principle will tell you that if you go exactly at a point, or taking the limit, you're going to find no phenomenon, no acceleration. But if you go a little bit bigger than that, you're going to find tidal acceleration. So really, gravity is not gravitational acceleration. When you take gravity and the equivalence principle very, very seriously, you see that the gravitational acceleration is actually, it's kind of a shimmer. It's not something that really, really exists. You have to look in a free fall frame and look locally and semi-locally, and you find that there's tidal acceleration, and that is the phenomena of gravity, tidal acceleration. So we now know that we need a theory not of gravitational acceleration A, but of tidal acceleration. Now clearly this is not a vector. We're talking about a relative acceleration of particles falling. The acceleration along here is a vector, but this phenomena of a relative acceleration and a relative acceleration along here clearly can't be a vector. Right? And in fact, they're components of a tensor. The radial tidal acceleration. Let's give this a name. So we're going to call them R. We're going to have some kind of R radial, whatever. The tidal acceleration components, these are three components of what turns out to be a tensor. So if we're going to say that we need a tidal acceleration theory, because there is no gravitational acceleration, it's fake, it disappears locally, we're going to need a field equation for the field quantities. Instead of the field quantity A, we have these three field quantities. All right? How would we write a tidal field equation for these three tidal field quantities? Now, we're going to have a problem because we're going to have a field equation. Something on the left side is equal to be 0 on the right-hand side. We're outside source. There's no source. There is a field. There's no source. So the source term is 0. We're going to have something on this side. Now, whatever you put here is going to be 0. Let's say R radial, whatever, is 0. Three quantities, and if you just set each one equal to 0, you have no theory. You have just 0, 0, 0. We have nothing. So that's clearly wrong. What can we do to get a tidal field equation? So I have this cloud of particles, right, arrayed in the sphere, and they're falling towards the Earth. Now what's going to happen to them? What will this spherical cloud look like a few seconds later?
It will stretch in the radial direction.
Stretch it in the radial direction. What else? Because all the particles in the radial direction are experiencing a relative acceleration.
First in the tangential direction.
Okay. So maybe do you know the answer already, or you
No,
just
you're
thinking about it now? Good. Okay. So clearly these are going to accelerate towards each other. As they fall, they're accelerating towards each other, and these are going to stretch. Correct? So what is this ball going to look like a little bit later? Is it going to be spherical?
more like a cigar.
More like a cigar, okay, or an oval or something like that, right? It'll stretch and compress more and more. Let's look shortly afterwards. So now this is a sphere, and a little bit later, when there's only been a little bit of change, it's elongated and compressed in, oval. Come up with a crazy speculation as to some kind of physical law that governs this shape, or something to do with this cloud. I don't want to give you the answer. Something that's beautiful that you have no way of knowing beforehand, but that, you know, it would be beautiful if such or such a law held. Okay, you have the sphere, and it elongates and compresses. So it was, yes.
Volume.
Okay, the volume remains the same. That would be beautiful if it happens, and in fact it happens, and it has to do with this divergence. Okay, it's a property of divergence. This becomes less, this becomes more, the volume remains the same. What does that measure? Obviously, we're taking into account some combination of these two things. Something is compensating for something else. On the one hand, it's getting more. On the one hand, it's getting less. The total remains the same. And that's reflected in an equation which takes the sum of these three things and adds them together and says that they're zero. Okay? It's a combination of these quantities which vanishes, not the quantities themselves. RT plus R theta plus R phi equals 0. This changes in one direction, these two change equally in the other direction. Okay, these become smaller, this becomes bigger, and the sum of the two, these two different types of tidal accelerations, cancel each other, leaving 0. And that's how we get around the problem in a local theory where you have three quantities, and if you just set each one equal to 0, you have no theory. It's a combination of these quantities which vanishes, not the quantities themselves. In Newtonian gravity, we know how to find the tidal accelerations given the gravitational accelerations. Okay? So one can easily work out this. How would you find the tidal acceleration components? Well, for spherical symmetry, it's a trivial problem. Okay, we kind of did it already. You have two particles neighboring here. One is falling this way, one is falling that way. Obviously, A minus A will be something like the derivative of A. Okay, you're going to get an A prime. If you do it rigorously, this will get. What about these two? What's the relative acceleration between them? If you do it, you'll find that you're going to get something with 1 over r there, because it's an angular difference between the two. And what it is 1 over r times A. Okay, it's a very simple problem to do in Newtonian, purely Newtonian gravity. So what we found are three components of the tidal accelerations, these three. Now I'm writing it like that. This is not a vector. It's just three components. It's really three components of a tensor. Okay, but for spherical symmetry we only need these three components, so I'm not going to worry about whether it's a tensor or not a tensor, and if there are some other components, these are the three interesting components that tell us everything that we need to know. These three quantities. I can express RT in terms of A prime, R theta and phi in terms of 1 over R times A. This was RT. This was, let's say, we'll call it R theta, and this was R phi. The tidal acceleration can be built up out of the gravitational acceleration. In other words, it has structure, it has a substructure. It's built up out of these things. And adds them together and says that they're 0. Okay? A prime plus 1 over RA plus 1 over RA equals 0. this changes in one direction, these two change equally in the other direction. Okay, these become smaller, this becomes bigger, and the sum of the two, these two different types of tidal accelerations, cancel each other, leaving zero. And that's how we get around the problem in a local theory where you have three quantities, and if you just set each one equal to zero, you have no theory. It's a combination of these quantities which vanishes, not the quantities themselves. Okay? Now, what do we see here? What is this equation? I did it from the tidal acceleration components. These are three components of what turns out to be a tensor, and I simply added them to reflect this property and so on. But where else do you find this equation popping up? Right here. In other words, this is the divergence of A. Okay? I didn't come to it from the divergence. I came to it by taking tidal acceleration components and adding them together in a beautiful way to take into account this fact that you can find experimentally, that the volume is conserved. And you find that what you end up with is basically divergence of A. So in other words, this equation, divergence of A is equal to 0 or equal to rho, if they're talking about inside the source, seems like it's a gravitational acceleration equation, but it turns out to actually be a tidal acceleration equation, something much more sophisticated. Just that the tidal acceleration can be built up out of the gravitational acceleration. In other words, it has structure, it has a substructure. It's built up out of these things. Therefore, when you express this equation of the tidal accelerations, you can express it not only, see here, this was RT. This was, let's say, we'll call it R theta, and this was R phi. So really my equation was what? It was RT plus R theta plus R phi equals 0. Right? These three quantities. I can express RT in terms of A prime, R theta and phi in terms of 1 over R times A. All right? When I do that, it turns into the gravitational acceleration equation because there is a substructure. It's actually a tensor. What we found here were just components. These two and these two will obviously be equal. Know that we're going to be talking about some kind of a warped time or warped space-time theory. We know what the acceleration maps do. The acceleration, which is the world line curvature, will be something like the geodesic curvature, the curvature of the straightest lines in this warped time theory. What will tidal acceleration map to? What is this phenomenon of tidal acceleration in the language of curvature? For example, curved surfaces. Okay? And the answer is really quite simple. You have phenomena where each of these is supposedly a geodesic, right? Each of these, it's a free fall, let's say this is a trajectory. If I draw the world lines for these two particles, right, and they're adjacent, and I'm looking at the spatial separation with time, how it changes. Each of these is supposedly a geodesic of the space-time. Of course, it doesn't look very geodesic here because this is a naive, flat space-time diagram. Really, there's a warped time that I need this warped space-time. In that diagram, which I can draw, these lines would be straight, or they would be geodesic. But nevertheless, although they are both geodesics, they will somehow have this, if I take a parameter along each one, right, like these cars moving along or these guys falling, right, I'm going to find that the distance between them is accelerating. Even though they're geodesics. Now, on a flat surface, in flat space-time and so on, if I just take this board in physical reality, right, if I draw two straight lines, they can intersect, they can be parallel, never meet and stay the same distance. If they intersect, then what's going to be, if I take a parameter along these lines and kind of move along with this parameter, what's going to happen to this distance between them, like the two cars on the road? What can you tell me about this distance? Is it going to accelerate? Or is it going to have a constant speed, or what? Clearly the distance changes, right? It's going to get larger as you move this way, or smaller as you move this way. But if you have the same parameter along this, then it's just going to be a relative speed, not acceleration. If you have curved lines like that, and you take the parameter, then there'll be an acceleration between them, even if you go with the same speeds as before. Okay? Now here we have something which is very odd. We say, not these are, of course, this is a space diagram. This is purely space diagram, so these are trajectories, not world line. This is the world line diagram. We're saying we have two lines which are allegedly geodesics of their space, and yet, nevertheless, there is this acceleration between them, which doesn't make sense because geodesics shouldn't have acceleration between them along their parameters and so on. You should have only constant velocity sets. When do you have this kind of acceleration? Well, in a flat space, you would have it if the lines are curved. That gives us an intuition to say, well, let's look at a curved surface and see what happens to geodesics. And in fact, on a curved surface, if you draw the straightest possible line on the curved surface, and then you take another one parallel to it at the beginning, and draw it straight as possible, you'll find that although it started out parallel, it's not going to necessarily stay parallel. And if you look at the separation between them, that separation can accelerate. In fact, some surfaces will take those two parallel lines and make them meet, which can't happen in a flat space. They can even meet twice. Okay, so if you have some kind of curved surface, you draw the straightest possible line, a geodesic, draw another geodesic parallel to it at some point, it's not going to remain parallel. And it can do all kinds of crazy things that parallel lines cannot do in flat space. So we have an intuition right away that this behavior of neighboring geodesics having relative acceleration between them, in other words, tidal acceleration, right away points to the fact that these must be geodesics of a curved space. Because only geodesics of a curved space can have this, what's called geodesic deviation, this acceleration of this distance between them. Okay? Sure.
If you take two lines that are not geodesic in a curvature space, they also will have tidal acceleration.
Then you can take in a flat space, and I can take these two lines and do whatever I want.
Yes, so you also have tidal acceleration.
You also have what?
Tidal acceleration between them.
I can always, on this blackboard in ordinary flat space, I can draw any lines and make them tidal acceleration between them. But that's not a physical phenomenon. That's just a result of my drawing this in a funny way. Well, but if it's not geodesic, it's not an interesting thing. But this is not a reflection of a physical phenomenon. What is a reflection of a physical phenomena is when two geodesics have this kind of behavior. Okay? Any other questions? In differential geometry, that measure of geodesic deviation is called Riemann curvature. Okay, if you take this, you call it eta, this distance, let's say, then eta double dot, right? That acceleration will be something with the Riemann tensor. Okay, that measures the geodesic deviation. So now we have a higher level theory than we started out with. We have a theory of geodesic deviation as a measure of curvature, rather than a theory of some kind of geodesic curvature, where we had an individual world line and we were trying to find the curvature of that world line. Now we're talking instead about something a little bit more abstract and more rigorous, not an individual world line and it's somehow its geodesic curvature, but take two world lines, each of which is geodesic, and find their geodesic deviation. Find the measure of the acceleration, so to speak, of the distance between them. So now we have a two-tiered structure. We have a theory with two geometrical levels. We have the acceleration, the gravitational acceleration, and we have the tidal acceleration. There's a tidal tensor, which in Newtonian theory doesn't have. I'll just use R for the tidal acceleration. Here this is really a tensor. And gravitational acceleration, which is a vector. Corresponding to this, we found the world line curvature. And in differential geometry, we know that we can only find the Riemann tensor components given these things in connection. And of course, in Newtonian gravity, we know how to find the tidal accelerations given the gravitational accelerations. Concept of geodesic curvature. So the geodesics are curved in this curved time, and if you look at it within a flat perspective, you're going to get curved world lines instead. If you think that the space-time is flat, you're going to see your world lines as curved. If you realize that that's not the case, then the curvature jumps over to the time, or to the space-time, and then it's the geodesics of that warped time which become curved. And the measure of that curvature is that which was the world line curvature. So you need one or the other has to be curved. Either you have your space-time is warped, your time is warped, and you have geodesic curvature, and then you can say that your world line is straight or geodesic, or you claim that your timeline is not warped, like ordinary Newtonian physics, but then you have to agree that your world line is curved. But the amount of that curvature should be the same for the Newtonian regime. Corresponding to this, we found the world line curvature, and then we said in the curved theory, it's not going to be world line curvature, it's going to be the curvature of the geodesics. And this maps to that geodesic curvature, all right? And we can see later that they're actually connection coefficients. In other words, somewhere in the geodesic equation, we're going to have something which tells us how the straightest lines of that space curve. For example, in a flat space, just let's say x double dot equals 0 is a straight line. That's the geodesic equation. Second derivative of x as a function of whatever parameter it is, or r as a function, right? That means the curvature is 0. That's a straight line equation. That's the geodesic equation. In curvilinear coordinates, the same straight line, but okay, so I have this tidal acceleration tensor, gravitational acceleration vector, and this maps to the Riemann curvature, right? The tidal acceleration is really geodesic deviation. This beautiful structure, 2 tiers, okay? We had the Riemann curvature based on the connection. We had the tidal tensor based on the gravitational acceleration. We know the geometrical interpretation of this is the measure of geodesic deviation. We know why geodesic deviation corresponds to tidal acceleration. It's these world lines which are deviating, and these world lines are geodesics, right? We know why the connection ties to the acceleration, okay? The connection is like a geodesic curvature, and this acceleration is the world line curvature, and one of them is going to be curved, one or the other. all right? Like the geodesic curvature in space. And that's going to map here. Now, this is all very, very nice, but it's not everything. There's a problem still, maybe not necessarily for this case. In this case, we had this was impossible to solve. We found there was a substructure. These things could be expressed, each one in terms of the substructure. And in the end, we knew that this is 1 over r. And we got a theory, we got a field equation just for this one gamma. So we have divergence of this is equal to 0. We know just ordinarily, obviously, if the divergence of some function is 0, that function is proportional to 1 over r. So we can solve this, for sure. If we have something more complicated, again, we're going to run into this problem. We have only one equation. Now, once one sees this beautiful structure, 2 tiers, okay? We had the Riemann curvature based on the connection. We had the tidal tensor based on the gravitational acceleration. We know the geometrical interpretation of this is the measure of geodesic deviation. We know why geodesic deviation corresponds to tidal acceleration. It's these world lines which are deviating, and these world lines are geodesics, right? We know why the connection ties to the acceleration, okay? The connection is like a geodesic curvature, and this acceleration is the world line curvature, and one of them is going to be curved, one or the other, all right? It turns out in differential geometry, some spaces, some curved spaces in which there is a Riemann curvature based on connection, also have a third level of structure, the metric. Okay? In some spaces, this gives you this, and in those spaces, one can find or derive the connection from the metric, and then one, of course, can find the Riemann curvature from the connection. So it becomes interesting to ask if that's the case in this theory. Of course, we know if we know general relativity, we know that it's the case. If we know special relativity, we know that spacetime has a metric, a flat metric with a metric. But I'm doing everything without any special relativity, and we don't know general relativity. So it becomes interesting to ask, if you know differential geometry, is there a structure like this in our theory? Now, what is the relationship of the connection to the metric? In differential geometry, it's very simple, well known. And we can see it, for example, let me write these 1 over r things that I spoke about. These are connecting coefficients. How do they come out of the metric? So if we take, let's say, an ordinary metric for flat space in Cartesian coordinates, looks like this. Again, no space-time, no curvature, nothing, just ordinary flat. If I write the same thing in curvilinear coordinates, all right, I'm going to get something like dr squared plus r squared sine squared theta plus r squared d phi, whatever, right? Now, once I introduce these things, the r squares and the sine thetas and so on, they're going to show up in these connections. We know that the connection coefficient is 1 over r. The way to get it from the metric is simply, you take, let's say, g theta theta prime over 2 g theta theta. Let's do that. G theta theta is r squared, or r squared sine squared. Take the derivative with respect to r. So you get the 2r over here, 2r sine squared over 2 r squared sine squared. The sine cancels out, right? You get the 2r over the r squared, and you end up with 1 over r. 2r over 2. See that? It's simple math. Okay? This g prime, this derivative is 2r, divided by twice the thing itself, so it's 2r squared. The 2 cancels out, and you have r over r squared, you just get 1 over r. Sine, the same thing over here. This becomes 2r over 2r squared, you just get 1 over r. All right? This is the connection coefficient, gamma r theta. So in differential geometry, one learns how to find the connections given the metric. Simple flat space metric. Given the metric, you do the derivative over the thing itself. There are other connections also. Sometimes you have to do g theta theta prime over g or r, or over g phi phi. I'm not going to get into them.
Okay, basically, we're just going to look at this thing. It's like G prime or G prime over 2. Like a gradient, something like a gradient or a derivative. Okay? So now the question becomes, is there anything in this theory which this is related to down here in the same way, this empty slot over here, in the same way that this would be related to this? We have a time warping theory. We know that it's time that's going to be warped in some way. If we're going to have something like a space-time metric, naively, again, without special relativity, you know, the natural thing to do is you would do this, dt squared, right? You'd say ds squared is equal to this. That's just the naive. Now, obviously, you need a scale factor to add speed, to add distances and times. You're going to have something with the speed over here, obviously. You don't know that c, we don't know the minus sign here, but naively, obviously, if you're going to have a metric of space-time, it's going to have something like a dt squared. All right? So it's going to look something like that. We know that we have a warped time. We know that in curved spaces, curved linear coordinates, curved surfaces, what happens is you get functions creeping in to these things. We certainly can expect that we're going to have some kind of function creeping into here. We're going to have a warped time. Right? It's a naive speculation, but it makes sense as a speculation. Then you have to test it, of course, rigorously. We're going to have something like that if we're having a warped time. So the question now becomes, let's assume that this quantity, right, it's really 3 things over here, which we didn't get to yet, but, you know, we define this as the worldwide curvature. Let's say in the higher level theory, we'll write it as this, to show that this is the curvature, this is the geodesic curvature in the curved space-time theory, rather than the worldwide curvature in the flat Newtonian theory. So we'll write it like this. All right? So we know that we have this quantity. We already see a reason to have this quantity in the higher level theory. We know that if it's derived from a metric, if there is a space-time metric, it'll be something like the derivative of this GTT. Just like this R theta is something like the derivative or derivative over 2 of G theta theta. All right? If it's a connection and it's derived from a metric, then it should be something like this. There might be also GTT below here or some other thing. I'm going to ignore that. Basically, GTT prime over 2. That's where the main physics will come in. So the question becomes, is there such a construct in Newtonian gravity which would lead us to suspect that in this higher level theory we have something like this? In Newtonian gravity, what is this quantity? Let me ask you, what does this quantity correspond to in Newtonian gravity? What does this boil down to in Newtonian gravity? This thing is the higher level geodesic curvature, which boils down to the worldwide curvature. Right? Either the world line is curved and the space is, and the time is straight, or the time is curved and the world line is geodesic. All right? So this is the curvature of the time in the curved time theory. It boils down to the gamma RT, which is the world line curvature in the flat theory. Which is what? In Newtonian gravity? What is the world line curvature? Acceleration. Gravitational acceleration. So my question becomes, in gravitational theory, is there something which is the derivative of something? Is A equal the derivative of something? Is the gravitational acceleration the derivative of something in gravitational theory? What's the answer? Of course, yes. Gravitational potential. So the natural thing to speculate is, well, we know that A is equal to phi prime. For spherical symmetry, just simply phi prime, radians, whatever. Right? So in gravity theory, there is this geometrical structure of the acceleration being a gradient of something else. We know in differential geometry that connections can be derivatives of metric if there is a metric in that space. It becomes very simple to speculate, at least. Let's test this theory and see maybe this is a theory of a metrical space. Not just a space with a Riemann curvature based on a connection, but a Riemann curvature based on a connection based on a metric. So you have a metric of space-time. And if one would in fact have such a theory, which of course one does, we would then expect what? We'll expect to see the following. We have a space-time metric, and remember again, this is, I put no special relativity in it, okay? ds squared, we had this function gtt dt squared plus the spatial part. What is this function gtt going to be? Well, we know that gtt prime is A, so what is gtt? A equals phi prime, which corresponded to gamma, this is gamma, prime equals phi prime. And we know that in differential geometry, this is that. So we can now relate these two things. In gravity theory, the acceleration is phi prime, which means that the worldline curvature is phi prime, which means that we expect that in our higher level theory, the connection will be phi prime. But we know that the connection should be the derivative of a metric coefficient. We have GTT prime equals phi prime. It's the same thing. And the connection in this curved spacetime theory, according to differential geometry, would be the derivative of the metric coefficient, in this case the time warping metric coefficient. And we know from gravity theory that that which corresponds to this connection is the acceleration, and that is in fact the derivative of phi prime. So phi prime is the candidate to be equal to GT prime. If that's the case, then GTT is equal to alpha plus beta phi, which means that we're going to stick it in here. So we have ds squared, the metric of spacetime, is equal to alpha plus beta phi, where phi is the gravitational potential, times dt squared plus the spatial phi. Where there's no function, this is totally flat in our theory, because we only have time warping. All we need is time warping to take into account the curvature of the world line, which is the acceleration. Now, this, of course, our intuition tells us that in the absence of any field, this should be 1. Correct? So we're going to have a 1 over here, and when this potential vanishes, it just becomes dt squared. So we expect this. So we've come all this way without special relativity. We've, in an intuitive way, we haven't derived, of course you can't exactly derive these things, and it's all post-hoc. People only thought of any of this only after Einstein came up with general relativity, and only years later when they went down in depth and understood well enough to see that a lot of this is in Newtonian gravity. Most of the stuff that I did here is not standard, right? Some of it comes up from my own thinking and ways of presenting and so on. Some of it is standard. And it's really, really nice how one sees that one can motivate the idea that space-time is curved, there's a connection, there's a Riemann tensor, and underneath it all is a metric, and that in the case of Newtonian gravity, you end up with this. One can even look at, well, this would get to too difficult a question. What is real? Like the tidal acceleration as opposed to the gravitational acceleration, or the connection as opposed to the Riemann curvature. Einstein actually wrote in some ways that seemed to point to his thinking that the connection was physically real, or that equally nothing was real, in the same way that the Coriolis forces are spurious. Gravitational forces are also spurious. It's a complicated question.